And the physics principles behind this lesson are very important for Physics 30. Not everything we study in Physics 20 is really that important in terms of Physics 30, but this is. We don't study satellite motion in Physics 30, but we study something different that's connected to it. So we're going to be solving satellite problems using Newton's laws of motion and universal gravitation, which Newton is also credited with discovering. So really, this is still an application of circular motion. We're going to be applying everything that we know about gravitation and circular motion to satellites. Now, when you talk about a satellite, you need to be careful here because there are natural satellites. The moon is a satellite of Earth because the moon is in an orbit around Earth. Earth is a satellite of the sun because the Earth is in orbit around the sun. We also have artificial satellites like Landsat and GPS satellites and scientific research and spy satellites that are in orbit around the Earth and other planets and other bodies. We have lots of satellites that are around the moon. Most natural satellites have orbits that are not perfectly circular, and normally I would study with you and teach you something called Kepler's laws of motion, which talk about non-circular satellite orbits. But I decided to kick it out of Physics 20 this semester to make room for more important things. There's something called eccentricity, and I'll explain it so you know what it is. If you have a circle, there is 0 eccentricity. If you have what's called an ellipse, there is a high degree of eccentricity. A circle that looks like this is not quite a circle. I don't know if you can tell by looking at it, but that thing is a little bit flatter than it is wide across. We would say that that eccentricity of that circle is very small. It's negligible. So we could treat it as being a circle. And we'll talk more about ellipses in just a minute. Isaac Newton has this idea. He knows that everything with mass is pulled by the force of gravity towards the Earth. Everything. And he looks up in the sky and he realizes, of course, that the moon has mass. The moon isn't made of nothing. The moon has mass. And that means that the moon must be, in his mind, accelerating towards the Earth. And he's right. The moon is accelerating towards the Earth. And he came up with this idea. He visualized the moon as falling around the Earth or falling towards the Earth, but the curvature ends up causing it to fall all the way around the Earth. It's a very hard thing to visualize. Basically, he imagined that if you stood on a mountaintop and you fired a cannonball, the faster you fire that cannonball, the further from the top of the mountain it's going to land. And that means theoretically you could fire the cannonball so fast that it would land behind you. That if this is the Earth, and I've got an animation here to show you in a second, but I would like to just explain it using my own words first. If this is the Earth, and there is some mountaintop up here, and he fires a cannonball, if it's fired slow enough, it just goes plunk and it lands. If it's fired faster, it will land here. If it's fired even faster, it might land here. And sooner or later, you'd be able to fire it fast enough so that it hits you in the back of the head. It's going so fast that the radius of curvature is going to match the curvature of the Earth. So there are a couple of links there in your handout. You can go ahead and look at them on your own time if you like, but I've already got one loaded. It's kind of a corny thing. There's a picture of the Earth, some kind of a diagram. There's a mountaintop, and that red dot is a cannonball. So I'm going to put the speed at 1,400 meters per second and fire this cannonball. and the cannonball falls. Right? It just falls by the base of the mountain. If I increase the speed to 19,300 meters per second, it's not coming back. And that's because 19,300 is greater than what we call the escape velocity of the Earth. Well, let's try 2,500. Goes a little bit further than it did before. If I increase that to 2,800, goes a little bit further. So we're going to have to really go up. Let's go up to 4,900. And it's still not going very far. I'm just going to sit at my computer and use a mouse. Let's go up to 5,500. Going a little bit further. I don't know what the sound effects are. 6,100. 6,400. We're getting close. It may look like we've got a long ways to go, but let's try 6,600. It's just got to kind of clear that right side of the diagram. 6,700. 6,800. Let's jump to 7,000. Not quite, so it's got to be a little bit more than 7,000. Let's try 7,300, 7,200. That's supposed to be the cannonball hitting the person in the back of the head. So at about 7,200 meters per second, it falls, but it falls all the way around the Earth. And that's what he visualized was happening to the moon. The moon has a net gravitational force towards the center of the Earth, but it's just moving at the right speed so that it stays in orbit. And we can start to answer these questions now, because the first question is, what speed for the cannonball results in a fairly circular orbit at an altitude, I don't know what that should say, at an altitude of, I know why this is the case. I had a different animation that showed the altitude, so we can just ignore all of this. Which speed for that animation shows a fairly circular orbit for the cannonball? That's what we are asked. And we saw that it was 7,200 meters per second. Now, what two possible things can happen if the speed is greater? I mean, we know what happens if the speed is smaller, right? If the speed is smaller, the cannonball lands on the surface of the Earth. Well, we have seen what happens if the speed is too great. If the speed is too great, it's possible that the cannonball leaves Earth's orbit and never comes back. But I want to show you that something else can happen. We said 7,200, it was fairly circular. I'll show that to you again, if I can get it. So this is the fairly circular orbit. Now, I don't know if you can tell, but it's not quite circular. Because if it were perfectly circular, the distance between the Earth and the orbit at the bottom would be a little bit more than it is. But that's okay. I'm going to go up to 7,800. And at 7,800, there's nothing special about the number 7,800. It returns back to the same place. And you might look at that and say it's a circle, but that second orbit is not a circle. it's called an ellipse. And if we increase this even more, there used to be an even better animation, but I couldn't find it. It's disappeared from the internet since the last time I taught this. You can continue to increase the speed and still get these elliptical orbits which become even more stretched out. It's going to come back, we just have to wait for it. And objects with these highly elliptical orbits are things like comets. You might have heard of Halley's Comet, which comes by every 77 years. Might come by again in your lifetime. They're in these really, really long orbits. And we're getting a little off track, but if this is the Earth, well, we'll say the Sun. If this is the Sun, Halley's Comet has an orbit something like that. And as it comes close to the Sun, which I need to move, as it comes close to the Sun, it goes faster and faster, and then it slows down. It goes very slow. And then it starts falling towards the Sun, and it increases its speed, and then it slingshots around the Sun. And the orbit is so... No, I don't believe Halley's Comet was last year. I think Halley's Comet was in the late 80s, and it's every 77 years. But we can look it up. We have time. There was another one. There was the Hale-Bopp Comet. I don't know why it's called the Hale-Bopp Comet. I want to say that Halley's was last around in the 80s. I remember big deal about it. Every 75 years, yeah, 1986. So add 75 years to 1986. You guys will be around, hopefully, to see it again. And by the way, these pictures, I remember being on a plane and seeing this. We were flying overseas at night, and the pilot said, if you look out the left window, you'll see Halley's Comet. And you see what this picture looks like. It's not like you're going to see this thing streaking through the air. It's like it's hanging there. It's so far away that even though it's moving so fast, it looks almost stationary. Well, there have been a number in the last little while. Usually when comets are in our vicinity, they make a big deal of them, and they end up talking about Halley's Comet anyway. So that's why, and Hale-Bopp was the late 90s, okay. That's why, Andrea, you're probably thinking Halley's because they always mention it. It's the most famous. Some of these comets, by the way, and we're way off track, but I don't mind talking about this. Some of these comets have orbits that are hundreds of thousands of years. It's hard to imagine. But we've encountered comets and we've tracked them, and using Newton's laws of motion and something called Kepler's laws of motion, we predict that the next time this particular comet will be here is in 238,000 years. Some of these orbits are just massive. When you start to look at astronomical distances, they're truly astronomical. That's where that word comes from in everyday usage in English. So anyway, what two possible things can happen if the speed is too great? One of the things that can happen is the object, I mean, we're talking about a cannonball here, but the object can leave the orbit of Earth. That's what we say. We say that it's going so fast, basically it comes up and doesn't come down. And the other thing is it can move. You can have an elliptical orbit. And I don't know, I want to play around with this just for a bit and see. I really spent a lot of time trying to find that old animation, which was much better because you could see everything in more detail. The Earth was very small in it. I'm going to increase this to 9300 and see what happens. So basically what's happening here is the object is going up, it's continuing to rise, and if I'm right, it's going to start coming back down sooner or later. Unfortunately, as it gets further and further and further from the Earth, the force on it will be less and less, so it will start to slow down more and more. We could be staring at this thing for 10 minutes, and I don't want to do that. So I'm hoping that even though I go to a different window now, it continues to grind away doing whatever it's doing. And if we hear that ouch sound, we will know that it came back. So now let's move on in the lesson. When a satellite is in a circular orbit, there is only one force acting on it, the gravitational force. This is the most important thing. I've written in your notes Fc equals Fg, and by now you know I harp on this. I go on and on and on about this. This is the net force. And I don't care about vector symbols here in this discussion of satellites. This is the net force. Why is the net force on the satellite the gravitational force? Because the force of gravity is the only force acting on it. And I think it was Evan who originally, when we started talking about directions of centripetal forces, he pointed out that it could be a force of gravity. It's exactly like the moon pulling an object, being pulled due to the force of gravity towards the center of the Earth. So this is the starting point when we do satellite motion problems. And this was the old animation. It's not the animation, it's just a clip of it. And what I could do in the old animation was I would just put my finger down here and I would swipe my finger very quickly in one direction, and it would cause that satellite, create a new satellite, and the new satellite would orbit. It would do things, and we could play around with the different speeds, but I can't find it, it's gone. So let's take a look at the first example. The moon is that far from the Earth. Determine the orbital speed of the moon. So what is that distance in meters? It's 3.844 multiplied by 10 to the 8 meters. Now, technically that distance given is from the distance of from the moon to the surface of the Earth, but we're just going to call it the radius. Usually, when you look up solar system data and you're told the distance between two objects, that's the distance from center to center. So we do not have to add the radius of the Earth here. By the way, the radius of the Earth is very small compared to that anyway. So determine the orbital speed. This is how you do it. You say that the net force is the gravitational force, and I'm going to ask you guys to ponder a question. I don't want you to type an answer yet, because I want to give everybody a chance to think of the answer. My question is, why is the net force the gravitational force? And if you truly understand the answer to that, you can answer it in about 5 words. But I don't want you to type anything yet. So now by typing yes, type yes if you feel you know why the net force is the gravitational force. For those of you that are still pondering it, I will throw one other idea your way. Net force means total force. Ben, would you be able to explain why the net force is the gravitational force? I mean, can you actually type a reason now? That's a good way to put it. All the other forces cancel out, and in fact, we can go even further here. What you've said is perfect, but there's a way to even... Oh, did you hear that? Did you guys hear that? Came back. I totally forgot about it. It came back. So it was an elliptical orbit, but you know, you have a hard time visualizing what I'm looking at here. I'm looking at a smartboard. Your screen is my smartboard. So if I had to estimate how far down that went, I might estimate that it went down like, oh man, 80 feet into the ground as it orbited around. So getting back to what Ben said, basically, because when you add all of the forces together, you get the gravitational force. And I will go even further. It turns out that since there's nothing in space surrounding the moon isn't moving through air, the moon isn't moving through mist, the moon isn't moving through rain. The force of gravity is the only force. This is the best way to answer this question. Yes, when you add all the forces together, you'll get the force of gravity, but it's because Fg is the only force. And again, I think you know me as a physics teacher by now. I'm more interested a lot of the time in the concept, because if you don't understand the concept, the calculations, you probably don't even get to the calculations. So where do we proceed from F net equals Fg? What I am going to show you is what we will do for all satellite questions. You go to your formula sheet and you say that F net is mass times acceleration. And then you say the acceleration is centripetal. So you do not have a formula that says F net equals MAC. You have a formula that says F net equals MA, and then we say centripetal. I have a question for you now. What I'm about to write, don't write. Why is writing mg wrong for the force of gravity between the moon and the Earth? Right. The acceleration due to gravity is not 9.81 where the moon is. If the moon was sitting on the surface of the Earth, well, that would be a ridiculous thing, right? If the moon were sitting on the surface of the Earth, then we would use 9.81. So Farhan quantified it by saying the gravitational constant where the moon is not 9.81, and Liam kind of summarized it in a general way by saying little g is the acceleration due to gravity on Earth. The moon is not on Earth. So what do we put for Fg? Well, capital G times the mass of the moon times the mass of the Earth over the distance squared. We use Newton's universal law of gravitation. Going a little bit further, I'm going to add a subscript of moon on the left because this mass that I'm pointing at right here, this mass that I'm highlighting, is the mass that accelerates, and it's the moon in orbit around the Earth, not the other way around. And I've changed centripetal acceleration to v squared over r, so we get m of the moon times v squared over r equals g, m of the moon, m of the Earth, over r squared. And now we have just a little bit of algebra to take care of. Again, I mentioned this to you the other day. We have gone from putting numbers into little formulas to building big formulas and then putting numbers in. The first thing that we can do is cancel the mass of the moon from both sides by dividing both sides by the mass of the moon. The second thing we can do is cancel one of the r's, because I'm just going to edit something here. Because r squared is r times r, we can multiply both sides of this equation by r and cancel an r with an r. Little bit of algebra here. This gives us the statement that v squared equals g times the mass of the Earth over r. Well, that's easy. What we did to get to this point is not easy, but to find v now is easy. V will be the square root of g. Look at the power of the things we're learning here. You can find out how fast the moon moves based on the distance from the Earth. Times 5.97 times 10 to the 24 kilograms. These are numbers I'm pulling off of the formula sheet. Once again, due to the complex nature of everything that we're doing with formulas and the numbers, I'm not worried about units in our work. And then divided by 3.844 times 10 to the 8 meters. And then you have to take the square root, so I'll give you a second to calculate that. And you can go ahead and type your answers in whenever you get them. Rounded to the nearest meter per second, 1,018 is the answer. That's a little bit more than a kilometer per second. I mean, you look up at the moon at night and it looks like it's hanging there, but it's actually moving quite fast. It would take the moon about 13 seconds to get from here, where I am in Wetaskiwin, to Millet. Any questions with the first part of example 1? Andrea got the same thing. Sienna, Evan. Okay, good. Let's move on. What's the orbital period? So that's asking how long does it take to go around the Earth? Well, I'm going to use v equals 2 pi r over t. We've already found the speed, so we can put the speed into our centripetal motion equation to find t. We're going to have the speed of 1018 is equal to 2 times pi times the radius divided by t. Basically, when you rearrange this type of equation, you can swap the locations of these two things. So I think my grade 6 teacher taught me this. If something is on the top of the left-hand side of this type of equation and you want it out of there, move it to the bottom of the right-hand side, and vice versa. So what we're going to have here is the period will be equal to 2 pi times the radius over 1018. And we're working in standard units. I'm going to go with the 1017.8. It doesn't really matter. And what do I have to do here? I have to go 2 pi times 3.844 times 10 to the 8 divided by my answer. And I get this number of seconds. So I'll just pause there. Anybody else get the same number of seconds? Okay. When we talk about time, a large number of seconds is not really meaningful to me. If I told you I'll be back in 2,373,016 seconds, you'd be a little perplexed about how long you have to wait. So if I divide that by 60, I get minutes. And if I told you, well, hang around for 39,550 minutes, you wouldn't be any happier about that. If I divide by 60 again, you get hours. Now you're starting to say, wow, that's a long time. If I divide by 24, because there's 24 hours in the day, you get 27 days, which of course is the cycle of the moon. The moon is in orbit around the Earth with a period of revolution of 27 days. The moon goes through its phases every 27 days. All right, any questions with B? All right, next question. Landsat is an Earth imaging satellite. There's a little picture of it there, or a little image. The altitude is 912 kilometers. What are the speed and period? So we're going to do the same set of calculations for this that we did for the other. And I'm going to pick up the pace considerably here. For a satellite in orbit, the magnitude of the centripetal force, which is the net force, equals the force of gravity. This is mv squared over r. This is g m over r squared. I want to pause there. Little m in my formulas is the orbital object, and big M is the Earth. Does anybody have any questions on how you would get to that statement? All right. Little m, which is the satellite mass, cancels. One of the r's cancels, and you are left with this statement: v squared equals g mass of Earth over r. So this is why I want to pick up the pace. I don't want to have to do this every time. You need to know how to do this. So if you're writing an exam, you're not worried about memorizing this formula. You're worried about finding the formula from a physics principle. I crossed out G because my brain slipped a gear. I should cross out little m. Yeah, that was an accident. So I don't even know what I need to do here for showing work, except to tell you that you need to calculate R by taking 912,000 meters and adding 6.37 times 10 to the 6 meters. Remember that R is the distance from the satellite to the center of the Earth. So we need to add those two numbers together to get R. It's 912 kilometers, so I multiply that by 1,000. Add the radius of the Earth, which is on your formula sheet, and we get this distance. That cannot be right, is it? No. We get this distance. I added an extra zero. I did add an extra 0 in my calculator, and that's what I should have written on paper, Andrea. Sorry about that. It's 912,000 meters. So when you take 912 kilometers multiplied by 1,000 meters in a kilometer, you get 912,000. So my mistake was in what I wrote, but I believe that what I entered in the calculator is correct. Good. So we get 7282000. Look, I'm not going to write all this down. Look at the formula. The formula is there. G is on your formula sheet. The mass of the Earth is on your formula sheet. And R is sitting in front of you because you have it written down or on your calculator. 6.67 times 10 to the negative 11 multiplied by the mass of the Earth divided by my radius of orbit, which is my previous answer. And then I have to take the square root. So I'm getting 7394. I'll give you guys a minute here and let me know what you get. Thank you, Liam. 7395, Evan gets. Andrew, you got the same thing. You know, and for goodness sake, don't try to memorize that formula. I suppose if you use it enough, you will know that V equals root GM over R. So that's the speed. Now what we're going to do, I'll just park that there for now. Now what we're going to do to find the orbital period is we're going to use speed equals 2 pi r over t. And again, I'm kind of being a little deceptive about this. I didn't announce it, but we've really gone away from putting numbers in and then rearranging to rearranging first. If I take V equals 2 pi r over t and rearrange it for t, I get t equals 2 pi r over v. Okay, that's a pretty easy calculation to do because we have v sitting right here on our calculator. 2 times pi times the radius divided by the speed The first thing I need is some feedback from some of you out there that do you get 6,187 seconds? Okay, good stuff. You know, we could write that as the answer. That's the answer in seconds. Again, sometimes it's useful for us to figure out what these things are in minutes or hours or days. If I divide by 60, it's this many minutes. Oh, okay, that's a good answer, 103 minutes. I don't think you'd want to go to hours. It's going to be 1.6 hours or something. You could, 1.7 hours. I think 103 minutes is a nicer way to describe what's going on here. Any questions with 2? All right. What is the length of one Mars year? So if Mars has seasons, and it does, how long does it take for Mars to return to its same place in orbit? Well, lightning quick here. I'm not even sure you need to write this down. F nets equals Fg. This is Ma. This is G, M of Mars, M of the Sun over R squared. Mars is in orbit around the Sun. The A is centripetal, so you get mv squared over R equals G, M over R squared. I mean, how many times am I going to do this before we just say, as long as you know how to do it, that's fine. So what you need to do, and I'm going to give everybody 3 or 4 minutes to do this, and I'll show you the numbers in a second, okay? Is you're going to have to calculate V in meters per second so that you can use V equals 2 pi r over t to find the time in seconds. That's what you're going to have to do. The table that I'm talking about has some information that you need. You need to know the mass of the sun, and you need to know Mars' orbital radius. The equatorial radius is the radius of the planet Mars. The orbital radius is how far away from the sun Mars is. Can you guys read that on your screen? Okay. So the mass of the sun is 1.99 times 10 to the 30 kilograms. The radius of the Mars orbit is 2.28 times 10 to the 11 meters. And again, what you were working on here, everybody, is finding the orbital speed in meters per second using the first formula so that you can find the orbital period in seconds. And we're going to go even further here, and I'm going to ask you to work out how many days the orbital period is. When you do find the number of days, I would just like to know that you've found the number of days. So when you do find the number of days, please type yes into the chat window. So we have a total of 23 people in class today. I'm not going to wait for all 23 to say yes, but I want to give people a chance here. To find the speed, you're going to take capital G, which is on your formula sheet, times the mass of the sun, divided by Mars' orbital radius. So Mars is a satellite of the sun. And then you're going to take the square root. Once you know the speed, to find the period, you're going to take this formula and change it to period equals 2 pi r over v, and that will give you the period in seconds. Then you have to figure out what you're going to get for days. And remember, when you do get the number of days, how about this? Even when you get the number of seconds, type yes. Incidentally, The answer to the question is on your screen right now, isn't it? The answer to the question, apparently, is this. Now we'll talk about any discrepancy we get compared to that in a second, because there might be one, and I know why there could be one. So while we're waiting, I'm going to start doing my own calculations to help people out who are maybe falling a little behind on this question. To find the speed, we take g, which is 6.67, multiplied by 10 to the negative 11. We multiply by the mass of the sun, which is 1.99 times 10 to the 30. And we divide by the radius of Mars' orbit around the sun, which is 2.28 multiplied by 10 to the 11 meters. A lot of numbers swimming around here. So you need to be careful and double check everything. I think I'm okay. I have to take the square root. I mean, that's phenomenal. Mars is so far away from the sun, but it's moving at over 24,000 kilometers per second. Or meters per second. I guess 24 kilometers per second. So, Liam, can you give me a thumbs up? That's what you got for the speed. Good. So this is what you should be getting for the speed. Again, I'll just park this here beside the letter V. For the period, we said that what we need to do is take 2 times pi times the orbital radius of 2.28 times 10 to the 11 and divide by our speed. So this is what you get for the number of seconds. If I divide that by 60, I'm in minutes. If I divide it by 60, I'm in hours. If I divide it by 24, I'm in days. So we're getting 687.19 days. And I would tell you that I believe the reason why it's off by not a whole heck of a lot, it's off by about a quarter of a day, is that Mars' orbit is not exactly circular. Which is why if you look at the top of this table, it doesn't say orbital radius, it says mean orbital radius. Mean doesn't mean tough, it means average. All right, we have one more kind of thing we want to look at today. We're probably not going to do the very final example. I don't know, how many of you have, type yes if you've heard the term geostationary or geosynchronous in terms of satellites. Probably not. A geostationary orbit is an orbit that a satellite is in so that it's always above the surface of the Earth. So what happens is I'm going to draw the Earth here from the North Pole down. So this is the Earth, this is the North Pole. It's where Santa Claus lives. And what happens, of course, is the Earth, be careful here, probably have my rotation wrong, it doesn't matter, the Earth spins. So this whole thing spins. Now, if I have a satellite in orbit, the satellite is rotating as well. And it could be that every time the Earth spins once, the satellite goes around 5 times. Who knows? It could be in a very low orbit, moving very fast. But the idea behind a geostationary satellite is this. I'm going to have to, how can I do this? When the Earth spins, the satellite spins at the same rate. And for this reason, these geostationary satellites must be above the equator. They have to be directly above the equator in order to have an orbital radius that can match an orbital rotation that can match the rotation of the Earth. Now, how long does it take the Earth to go around once? 24 hours. So basically, a geostationary satellite has an orbital period of 24 hours. And if I'm standing on Earth looking up at this satellite, this is my eyeball, that satellite will appear stationary because as I move with the Earth, the satellite moves. So that's what a geostationary satellite is. Why might we want geosynchronous or geostationary satellites? Well, communication satellites, spy satellites, I won't ask you to type yes if this is true, but I'm sure some of you have satellite dishes attached to the side of your house. And those that don't understand, there are these things that are called satellite dishes that you can pick up signals to watch TV shows and to get internet. Well, the idea behind them is that your dish is pointed up at a satellite that is sending the signals, but if that satellite moves in the sky, then you would have to be out there moving your dish all the time. So what you do when you install the satellite dish is you point it at the satellite, and if you've ever done it, it can be a very frustrating thing because if you move it just a little bit, you're way off. And the result is that it's always pointed in the same location. A spy satellite, there's probably a spy satellite pointed down at the Kremlin in the former Soviet Union in Russia right now, that's always watching the Kremlin. Okay, we're going to do one question here. We're not going to do question 7. I'll talk about that in a second. What altitude must the satellite orbit around Earth so that it's geosynchronous? This is MA. This is G, M over R squared. What have I been teaching you you put in for A? I've been teaching you put in V squared over R. Is there something else we can put in? There's that other formula that I normally don't like, but we're forced to use here. And I need you to go to your formula sheet and double check to make sure that that's correct. So that goes in where we have AC. And things are going to take a step up here in terms of complexity because now look at what we have. We have the mass of the satellite times 4 pi squared r over t squared equals g times the mass of the satellite times the mass of Earth over r squared. Got pretty complicated pretty fast. But that's okay. The masses of the satellites still cancel. And we can cross multiply. I take 4 pi squared r and multiply it by r squared. And I take t squared and multiply it by GMM and set them equal to each other. So I get G times the mass of Earth times the period squared equals 4 pi squared r cubed. Nobody's going to memorize that. R cubed will be equal to G times M times T squared over 4 times pi times squared. There is no simple way for you to chip away at this problem by calculating one thing and going on to the next step. This means that r is equal to the cube root of that mess. And I know that this is a long lesson, but as I started off this lesson by saying, it's important for Physics 30. And I want you to follow along with something that's very important right now. We're going to take a very tiny detour because I don't want you to make a mistake based on not knowing how to use your calculator. I would like everybody to take 100 on your calculator. I want to know the value of this. I would like you to take 100 divided by 4 pi squared and figure out what it equals to. And I seem to recall we did this somewhere already, but well, I'm glad that the first couple people who chimed in are getting 2.53 because I believe that's what it is. If you do this, what I'm about to do is wrong. If you do this, then you will be dividing 100 by 4 and then multiplying by pi squared. This is not correct. You need to have the 4 pi squared in brackets. And you get 2.53. Okay, so let's calculate together what where did it go? I guess I'll have to rewrite it. Can you help me out? Is that what we had? Thank you. I must have erased or cleared my board somehow. So I would like everybody to calculate what is underneath the square root sign or the cube root sign. I just want to know what this is, and then we'll talk about how to find the cube root on your calculator. I'll do the same thing up here. I won't be asking you to type your responses. So you can do it on your own or you can follow along. We want to take the universal gravitational constant and multiply by the mass of the Earth. Then we want to multiply by the period squared. Well, it's 24 hours, everybody. The period is 24 hours. So if you want to, you can take 24 hours times 60 and figure out what that is. If you take 24 times 60, you get 86,400 seconds. 24 hours is 86,400 seconds. So you could do that on the side, or what I was just going to do is put times 24 times 60. Well, I need brackets because I have to square it. 24 times 60 times 60. I have to square that t. So there's my g times m times t squared. I need to divide by, in brackets, 4 times pi squared. I will double check all of my entries because there's a lot of numbers here, but I get this number. Does anybody else get that number? Okay, good. Now we have to take the cube root. And I don't want to get into a math lesson here, so I'll just tell you, if you go into your math menu, there's an option number 4 that is the cube root. So we take the cube root of the answer, and we get this for r. Unfortunately, this is like zombie physics. You think you're done and it just keeps coming back for more. That's not the answer to the question. What are we going to have to do to determine the answer to this question? Well, it said, what is the altitude, which is the distance above the surface of the Earth? So what we have determined is that if this is the Earth, the distance from the satellite to the center of the Earth is this number. What we are after is called the altitude, which is the distance above the surface of the Earth. We have to take that whole distance, this distance, which is r, and subtract the radius of the Earth to get the altitude. So if we subtract 6.37 multiplied by 10 to the 6, this is the altitude above the surface of the Earth. So it works out to approximately 3.6 times 10 to the 7 meters. There's more that I wanted to talk about today with regards to these geostationary satellites, but we will get to that tomorrow maybe. I know that's a long lesson. We're not going to do the next example, which weirdly enough goes from 5 to 7. 7 asks you to do the same thing for a satellite around Venus. Just in summary here, the net force for a satellite is the same as the gravitational force between the satellite and the body it's in orbit around. This is ma, always. This is g, mass of the satellite, mass of the central body, over r squared. Most of the time, you put v squared over r in for a. Unless you're trying to find r from the period. So instead, for a, you can put in this, the seldom used formula, instead. Whether you go this way or this way, the mass of the satellite cancels. It's pretty powerful stuff in terms of applying physics that, we've kind of creeped up to this level that you're able to now do astronomical calculations with regards to celestial bodies. As I said, we're not going to do 7. I would definitely say that you should know how to do the 3 problems that are attached. You can pick and choose a couple of the other problems. You only have about 15 minutes left before class officially ends, but you know the drill. I'm here until 11:30. I know that was a packed lesson. We've gone an hour and 45 minutes, probably about an hour and a half, hour and 15 minutes on this lesson, but disregarding the length, when you talk about the content, too fast, too slow, or just right, please.